Hello, my name is Karthikeyan Rathod and today in this video I am going to talk about breadth first search algorithm. Breadth first search algorithm is a graph traversal algorithm. There is another graph traversal algorithm which is known as DFS, depth first search algorithm. But in this video I am going to talk about breadth first search algorithm BFS. BFS is particularly useful for one thing, that is finding out the shortest path on an unweighted graph. Introduction of breadth first search algorithm. As you can see in the first example, an undirected graph is given to us. It is a non-cyclic graph and our task is to do BFS from the source vertex 0. So first, breadth first search algorithm is similar to a level order traversal. So first, we will print the source vertex and then all its neighbor. So as you can see, 1 and 2 are its neighbor, so we will print 1 and 2. And then we will print their neighbor. So as you can see, one has 0 neighbors and 2 have 2 neighbors, that is 3 and 4. So we'll print 3 and 4. In the second example, you can see an undirected graph is given to us and it is a cyclic graph, and our task is to do BFS from the source vertex 0. So first of all, we will print 0 and then all its neighbor. So first, as you can see, 1, 5 and 2 are its neighbors, so we will print 1, 2 and 5, and then we will print their neighbors. So as you can see, 1 have neighbor 3, so we will print 3, 2 have neighbor 4, so we will print 4. So this is how BFS works. So now we will move towards the idea of breadth first search algorithm. The idea of breadth first search algorithm. As you can see in this graph, an undirected graph is given to us and it is a cyclic graph, and our task is to do BFS from the source vertex 0, s is equal to 0. So first of all, the idea of breadth first search algorithm includes that we will use a queue data structure and a visited array so that we do not visit the same vertex twice. As it is a cyclic graph, it may happen. So it will happen. So for simplifying, I have added all the neighbors to the corresponding vertex. So as you can see, 0 vertex has neighbor 1 and 2, and 1 vertex has neighbor 0, 2 and 3, and 2 vertex has neighbor 0, 1, 3, 4, and 3 vertex has neighbor 1, 2 and 4, and 4 vertex has neighbor 2 and 3. So first we will enqueue the source vertex, that is 0, in the queue, and then we will mark it as true, that we have visited 0. Also we will have an output screen in below right here. So first of all, we will dequeue 0 from the queue and enqueue all its neighbor. So we will dequeue and then print it in the output screen, and then enqueue all its neighbor, and we will check if the neighbors are visited or not. So as you can see, 1 and 2 are false, so they are not visited, so we will enqueue 1 and 2. And then we will mark them as visited. After this, we will dequeue 1. After this, we will check if the queue is empty or not. If the queue is not empty, we will continue. So as you can see, the queue is not empty, as there are 2 elements in the queue. So first we will dequeue 1 from the queue and then print it in the output screen and enqueue all its neighbor. So as you can see, its neighbor are 0, 2 and 3. So in this you can see that 0 is already visited, as it true, and 2 is also visited, it is true, but 3 is not visited, it is false. So we will enqueue 3 and then mark it as true. After this, we will dequeue 2 from the queue and print it in the output screen and enqueue all its neighbors. So as you can see, its neighbors are 0, 1, 3 and 4. 0, 1, 3 are already visited. True, 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 true. But 4 is not visited, it is false. So we will enqueue 4 and mark it as true. And then we will dequeue 3 from the queue and print it in the output screen and enqueue all its neighbor. So as you can see, its neighbor are 1, 2 and 4. And 1 to 4 are all true, so they are all visited, so we will not enqueue anything from it. Then we will dequeue 4 from the queue and enqueue all its neighbor. So and then print it also in the output screen. So as you can see, if we try to enqueue 4 in the queue, you can see 2 and 3 are its neighbor and they are already visited. So we will not enqueue anything and our loop will finally terminate because our loop was till the queue is not empty, but now queue is empty, so we will terminate and it is our output. Implementation of breadth first search algorithm. So first, as you can see, here is the breadth first search function and there are 3 arguments. So first argument is the vector argument, which is a dynamic array of edges and vertex and source. Here edges, as we have seen in the previous slide, edges is this, where at the 0 index all the neighbors are present, at 1 index all the neighbors are present, 2 index you can see 0, 1, 3, 4 neighbors are there. So first our vertex is 4 here, as you can see, the last, and the source is 0. So first we will initialize the whole visited array as false. So as you can see, 0, 1, 2, 3, 4 is initialized as false, and we will first initialize queue data structure as queue, and then we will enqueue 0 into the queue and mark it as true, the source vertex. Now we will check if the queue is empty or not. As you can see, the queue is not empty. So we will take the front of the queue, which is 0, and then we will dequeue it from it, and then we will print it in the output screen. 0. Now we will iterate over the whole neighbors of source vertex 0. So which is 1 and 2 are the neighbors of 0. So we will check if 1 and 2 are visited or not. As you can see, they are false. So we will enqueue into the queue and make them as visited. So first we will enqueue them 1 and 2, and then we will make them true as they are now visited. So we will check now if the queue is empty or not. As you can see, the queue is not empty. Now we will take the front of queue, which is 1, and then dequeue it from it and print it on the screen. Dequeue is this part and then printing is this part. Now we will iterate over the whole neighbors of 1. So as you can see, the neighbors of 1 are 0, 3 and 2. As 0 is already visited, so we will not go in the if condition, and 2 is also visited, so we will not go in the if condition. As 3 is not visited, it is false, so we will enqueue it in the queue and make it as visited, and then now we will check if the queue is empty or not. As you can see, queue is not empty. Now we will now the front part of the queue is 2, and we will dequeue it from it and then print it on the screen, output screen. Now we will iterate over the neighbors of 2. As you can see, the neighbors of 2 are 0, 1, 3 and 4. 0, 1, 3 are already visited, but 4 is not visited. As you can see, it is false. So now we'll make it true and enqueue it in the queue. Now we will take the front of the queue, which is 3, and then we will print it on the screen. and then dequeue it from the queue. Now the neighbors of 3 are 1, 2, 4. 1, 2, 4 are already visited, so we will not enqueue anything into the queue. It will not go into the condition. So then we will dequeue 4 from the queue and then print it on the screen, and then we will check if there are neighbors of 4 which are not visited. So as you can see, neighbors of 4 are 3, 2, which are already visited, so we will not go to the new condition, and our loop will break because now the queue is empty. So this becomes false, and then we come out of the loop, and this is the outputs. Now let's talk about the time complexity of breadth first search algorithm. The time complexity of BFS is big O of V plus E, where V is the number of vertices and E is the number of edges. Let's see the BFS code. As you can see in the BFS code, in the innermost code, you can see that we are traversing through all the adjacency list of every node. So if we find out the sum of length of all the adjacency list, then we know the time complexity of BFS. So as we know that the sum of length of all the adjacency list is twice the number of edges in the undirected graph, and the sum of length of all the adjacency list is equal to the number of edges in directed graph. So through this concept, we can find out the time complexity of BFS. Let us see an example graph to understand the previous topic. So as you can see in this graph, an undirected graph is given to us, and it is a cyclic graph. So our task is to find the sum of all the length of the adjacency list in this graph. So as you can see, how many items will be there in the adjacency list of 0? There will be 3 items, 1, 2 and 3. So 3. In the how many items there will be in the adjacency list of 1? There will be 2, 1 and 2. And how many items there will be in 3? That is 3. As you can see, 1 is the neighbor, 0, 2 as the neighbor. So the length of the adjacency list of 3 is 3, and the length of the adjacency list of 2 is 2. As you can see, 0 and 3 are the neighbors, so the length is 2. So the sum of all of this is 10. So as we talked earlier, that the sum of length of all the adjacency list in an undirected graph is equal to twice the number of edges. So as you can see, there are 5 edges, 1, 2, 3, 4, 5. So twice the number of edges is equal to the sum of all the length of all the adjacency list. We know that the time complexity of BFS is big O of V plus E. So as we know that E has come from this inner statement, but how did we get V? So let's find out. How did we get V, and why are we adding V in the time complexity of BFS? So there can be a corner case. As you can see in this graph, a graph is given to us, and this graph is completely disconnected and there are no edges. But still we have to use BFS. Still we have to apply BFS on every graph, still even if there are no edges. So that's why we are adding V in the time complexity of BFS.